Okay. Okay. It looks like it's working. It looks like it was working both times. Okay. So now let's. We've got that up there. I'll post that, and so you can continue on to finish Lab 9. So now we're gonna talk about the new stuff for today. Now we're moving on a little bit. We're changing gears in terms of what we've been talking about. So there are two major data models in ArcGIS. There's the vector data model, which we've been dealing a lot with up to this point, and there's the raster data model. Okay, the raster data model thinks about the world as a models the world, I guess is a better way to say it, as a continuous set of evenly spaced numbers. It's always numbers. Those numbers can actually represent things that aren't numeric, like they can represent presence, absence. They can represent a code that represents a non-numeric value, like a land cover. They could represent, like 5 can represent forest, and 6 could represent agriculture. But they can also represent real numbers, such as things like elevation or temperature. In any case, the raster data model is, sometimes you just say it's a picture. It's a lot like a picture. In fact, if you take a picture nowadays, it's always digital, and it's rows and columns of numbers that represent the amount of reflectance at that particular location in the image. All right. So our GIS. This isn't an introductory GIS class, so there's a lot to talk about there, but ArcGIS allows us to manipulate raster data sets. And hopefully you've taken a course where you've talked about that a little bit, but if not, we'll do a short review here. It allows us to manipulate data sets. We could take a data set and we could do some math to every single cell individually to create a new raster data set. So there's always, it's like math. There's an answer and there's a function behind it. Oftentimes we categorize the functions into 3 different types of functions. If we're just thinking about the individual cells and we're changing the individual values of a cell row by row, then we call that and column by column, we call that a local operation. So if we did have a grid that represented elevation, and we changed the elevation from feet to meters, we would have to multiply all the grid cells by 3 point something. I think it's 3 point something. Anyway, that's not really important, but we have to multiply every cell by a certain amount to get meters. Okay. All right. Neighborhood operations allow us to usually compare every cell to its neighbors in a function. One of the most common examples of that in a GIS is to calculate slope. So we calculate the slope of a single point cell by cell. We're comparing it to its neighbors and seeing how quickly the data set is, in this case, elevation, how quickly elevation is changing at that location. That's a measurement of slope. That's what slope is. It's the measure of how quickly. So in calculus, you might call it the derivative. But we don't calculate it using calculus. In this case, we just look at its neighbors and calculate a value. All right. The last category, well, not the last category, but there are a number of data sets that are, a number of functions that are called zonal. And zonal operations allow us to summarize a raster data set by an area. So we can say, what are the average values for a certain data set or categorized by a certain data set. So we might want to know what the average values in every city is, what the average elevation in every city is, or the average, the total population in each state is, if we had a state that was a raster data set. And then there are some global functions such as finding distances and things like that. All right, let's do some examples in Python, and we'll talk about a few of these other things when we do that. Okay. So for this, I've actually uploaded a number of data sets. Some of them are huge, humongous. Well, not that big, but they're big. They're big, almost too big to deal with. So if you want to download basically all of these data sets, this is what we're going to do for the lab. This is the data for the lab, and this is the data we're going to experiment with. I'm going to start with this smaller one, WSB DSM. So go ahead and download those data sets, and we'll use that to explore raster data. So if you just hit view raw, it'll download it. Climate data, view raw. Yeah, that's not that huge. It always takes longer to upload. So when I uploaded these data sets, it took like 10 minutes. But downloading is faster, even on campus. But all right, so I'm going to go ahead and show all three of these in a folder. And I'm going to copy these to... The reason that I don't copy them to the same place that I work in is that if I put expanded data sets in those in SPA, then it will upload the expanded data set and it'll be huge. So I'm going to create a new data set and call this Lab 10, or I'll just call it Week 10, and put them in there. And I'm going to extract them all. So I'm going to take this data set, extract it, the USA data set, extract it. What are some file formats for raster data? TIFF is one, yep. You saw that on there. LEZD. Okay. All right. Mr. SID is SID usually, file extension. Now these, you can actually store a raster in a file geodatabase, which is what's happened here. I'm going to look at some of these data sets in here. So I got a SPA, rename or refresh. I got week 10 going on. Okay, so here's one of the data sets. This is a very, very zoomed in data set. It's just a subset of the very corner of Walker Science Building. Anybody know? Can you guys kind of see which corner? For those of you up here that are familiar with Walker Science, this is still north at the top. So which corner would that be? The brighter areas are the higher elevations.
What data set is that one, Dr. Egger?
It's called WSBDSM.TIFF. I'll put it in here, and maybe change the symbology a little bit. So yeah, it's the southwest corner. Okay, so this is the building itself. This is the facade. The highest thing there is the facade on the front of the building that says Walker Science as you're walking up to it. Okay, and then we know that this slopes gradually down. Right, there's This is actually the cutout for the people walking up and in that way. And then these are big oak trees. There's like a little podium right here. Have you ever noticed that? As you're walking in that corner of the building. I don't know why there's like, it's not even, nobody's noticed it. It's just like this little thing, and it has like a little, so you could like talk to people.
You could like have a speech.
You can have a speech right there in this corner of the. People could stand out here and listen to you. Yeah.
Safe space.
Yeah. So if we ever want to have class outdoors, then I'll just go out there, I guess. Okay. And this is like, the building gets taller or something. Maybe there's a air conditioner. I don't know. But that's what this data set represents. So it's not a bare earth. Okay, but we can use this just for fun as a data set to mess with Raster. Okay, so I'm not sure that you have to import inside of ArcGIS, but I'm just typing import. Actually, it's here. I've got the desktop help here. It's a little bit different. It's a from statement. Okay, so from ArcGIS or ArcPy, from ArcPy import ArcPy.sa. No, just import star. Yeah, that's sorry. From ArcPy.sa, import star. Okay. I'm not sure you need to import it here, but we're going to do it anyway. So from ArcPy.sa, this is another submodule to ArcPy. And this is the way that all the help is written to import this statement. What this allows you to do is use any function as if it was an actual function. So the slope function becomes slope parentheses and it works. So it's a little different than the way that you use the other tools in ArcGIS. Since we're dealing with numbers themselves, we're just taking numbers, inputting them into a formula, and getting numbers out. And that, when I say numbers, I'm talking about rows and columns of numbers, and ArcGIS calls that entity a raster. Okay, a raster is a new data type now that we're talking about. So a raster is the digital representation of this data set. So I just press enter. If I want to create that digital representation, I have to actually type it. So I type in raster, and this is a function that takes a path, or in this case, I can just use the name of the layer. Okay. But let's put in the full path, just because that's the way we'd have to do it in a script. So I'll put that right here. It'll work just the same. So I'm going to use the R, and now I have the full path to that raster. And now once I hit enter, I'll have created that raster. The only problem is I didn't assign it to a variable. So let's redo it. And we'll call this WSB DEM equals raster. Now I've got it, and it's being stored in this variable called WSBDSM. So if I want to calculate the slope, I can just feed it now that variable. But I can only give it rasters. It doesn't take, it's not like the other one where it takes, it does take a path and do just fine. So you have to feed it a raster. If you don't, sorry, I guess what I'm trying to say is, you could put this whole thing, do that over here. You could put this whole thing inside of it. That would be perfectly acceptable. You can nest a function inside of a function, just like we've we've done before. But you do need to put that function there so it'll turn it into it. Oh, also I want to save it as something. Slope WSB is equal to slope WSB DEM. Oh, I didn't spell WSBD. Python is case sensitive, so I spelled this like this, which is inconsistent of me. Usually I don't do that. So now I hit enter, and it ran. I don't know why I'm getting an error there. I was getting all sorts of errors in my last class, but I figured out that most of them were my own fault. That should work.
Dr. Rader,
Yeah.
I know this is going to be taking you off course, but is there any way you might be able to change your display settings?
It's too
very,
small.
very-
Okay. Well, I think what I'll do is just put this in a script. I'd hope to do it that way, but let me just put this in a script. And then it'll be bigger for you all. And we can always just go back and forth and look at it. All right. So I put all that into a script like that. And that should work. I'm going to be more consistent and make this DEM. Is that a little better?
Yes, sir.
Yeah. Okay, let's see if this.
It's real tiny on YouTube or something.
Yeah, and ArcGIS is not like it. I can't correct it. If you make the display bigger, it still makes everything bigger, but ArcGIS, the words don't get any bigger like they do with other programs. It's annoying. All right, so I'm going to try to run this. I'll save this as, I'll save this in week 10 and call this example 1. Example 1.py. See if we have the same error. The slope tool is not licensed. Oh yeah, something I forgot. So we haven't encountered this before. We're actually trying to run a tool that it has a separate license on top of ArcGIS, and so the help does talk about it. I just glossed that over. But you do have to license, make sure that you license the tool. It's in a different help. It's called Checkout Extension. See if this works. Checkout extension allows you to actually physically check that box and say, I want to use or consume a license of Spatial Analyst, because Spatial Analyst is a separate extension. So I forgot about that, but there you go. So we need to check out the Spatial Analyst extension, and you'll have to do that in all your scripts where you want to use Raster, because ArcGIS licenses those tools separately. Okay. All right. Now that didn't fail, so I don't know why it failed in ArcGIS. I do know that I've had some programs failing inside of my laptop recently. The desktop works just fine. Okay. So that ran. Where did it save slope WSB.dem? It's a trick question. It didn't save it. Okay? So a raster is an in-memory object all the time. It doesn't store it on disk. Occasionally, if you don't have enough room in your memory, ArcGIS actually does save it onto disk, but it doesn't tell you where it is. And as soon as the script finishes, it's gone. Okay? So the help actually talks about that. That's other class. Is it the same window though? And I'm gonna go ahead and close a lot of this stuff. Okay, there it is. The help talks about that, creating a raster. This is the same link that's up there. So we talked about creating a raster object. We ran slope, but we didn't do this part, the raster save method. If you want to save it onto disk, you always have to do this. So this will actually save an output raster. So any raster has this function. Sometimes we call it a method when it's attached to an object. So any raster object has the ability to be saved using the save function. All you have to do is give it a path. And it has to be a valid path, otherwise you're going to get that error. So let's save this somewhere. So I'm going to put this here and say save. Or sorry. It's not, I didn't call it out raster, I call it slope WSB. So I need to feed it that, dot save, and then I need to give it a valid path. So here's the path to my other one. And now I'm just going to call this WSB slope. It's going to change WSB DSM slope.tip. So now it'll save this data set out to a new data set, and it'll be on disk. So I can run that. And when that runs, it ran. I should be able to see it over here. If I refresh, yep, there it is. Now, that doesn't look very, well, I mean, it does look like it's supposed to look. Okay, what are the bright areas on there? Those are high slope areas, exactly. And so we see in the trees, there's a lot more high slope areas. It's probably where the canopy just drops off right there. So even up in the top of the canopy, there are different layers to the canopy, and every time there's an abrupt change, we get a line. So this is the very edge of the canopy. This is another edge of the canopy. These are edges of the buildings. Okay? This is the edge of that higher roof line. Okay, these little circular things are just pipes sticking up out of the ground. I don't know where that little podium is, but it's somewhere under there. Can't see the slope of that. So that is just a little code snippet, and all it does is read a file in and calculate the slope on that file. Now, I don't know why we would do this, but you can do any math that you can enter into a raster calculator in Python. So we could take the slope of WSB and add it to the original layer. Okay, WSB DEM. So you can add two rasters together just as if you added two numbers together in Python. So would you just call this sum for some reason, or total? The sum looks like a reserved word. And then we could save this out here. because this is still a raster. Remember, we have to save it if we want to actually see it, and call this total. And I'm going to save this as example 2. So now I'm going to run that guy. I'll go back to here for a second. Now, it's not doing anything. It's not going to do anything in here because I don't have any print statements. But I'm adding the actual elevation to the I don't really need this line in here anymore, so I'm just going to delete it. But how would I change this if I wanted to delete it? Well, I could do overwrite. I always forget how to spell overwrite. There we go. So I don't need that line in there anymore because now I'm just adding those 2 lines. So you see how it said it exists and you can't overwrite it since we didn't tell it explicitly could. So now we're telling it explicitly could overwrite that value. Did it finish? I think it finished. So now we should have another data set that's just refresh. The total. So the total is the slope plus the original. It doesn't really look that great. It doesn't look like anything changed, but anyway, that's adding 2 things together. Hey, maybe a better example would be, we don't have to change this much. So I'm going to save this as 3. And something that people actually use is they take the neighborhood mean and they subtract the original data set. And the neighborhood mean minus the original data set it's one way to extract a texture measurement from the data. So we've calculated slope, but let's, instead of calculating slope, calculate the neighborhood mean value. So let's look at how to do that. Because this will also give us practice in looking at how to calculate or how to look at the help for raster stuff. Raster stuff. There's got to be a better word for that than that. We'll call this example 3, and instead of calculating the slope, we're going to calculate a neighborhood mean. Okay. So all the tools for raster, for those of you who haven't taken raster GIS course, are here in the spatial analyst tools. We're going to look at neighborhood, and we've got the focal statistics. The focal statistics is where all the neighborhood values are. So if we want to hit tool help here, there is some help on how to do this using a using ArcPy. So see how there's an ArcPy example, and there's the arcpy.sa import, and here is how to set up a focal statistics. You do have to feed it you have to create something called a neighborhood rectangle. A little bit of a new twist there, but you're feeding it a neighborhood rectangle. You're giving it a height and a width, and you're telling it to use cell as the cells, not distance. So we could, if we wanted to implement this, just copy. We actually don't need this line right here. We just need these lines right here. Okay. Go into my code. Remember, I've already saved this as example 3, so I don't need to change this too much. So now, my raster data set, I already have that. I already have this. So I'm going to say, I'm just going to do a 3, 3. And then my focal statistics are, I'm going to do a mean instead of a majority. I don't need that last. So I'm going to feed it that neighborhood. My in raster is going to be my WSB-DEM. So what I'm doing is taking that Walker Science Center, Walker Science Building DEM, and I'm going to get the neighborhood mean. It's basically, what does the neighborhood mean do for those of you who've taken a course? And it averages neighborhood, but what's the result look like? The result looks kind of like the input, but it's more fuzzy. It averages all of the nearby points and assigns them to the center value. So it's okay, in Photoshop, it's the blur tool. That's exactly how the blur tool works. So it blurs an image. All right, so we're blurring a 3x3 area, which is going to go really fast, but it might not produce much of a value. So then if we blur the original value and we subtract the focal statistics value from the original DSM, then we'll see those areas that were changed the most by the blur. So that's what we're doing here. So the high values have been changed a lot by the blur, and the low values haven't hardly been changed by the blur. So it's used a lot for edge detection. It's going to actually be fairly similar to slope. I mean, because slope is also kind of like detecting edges. But it's not going to be the exact same. So I'm just going to call this edge here. But it's not looking in any specific direction. It's looking all around it to find the blur. The blur is in any direction. So I'm going to run this guy. I don't know if I think it ran already. The one reason why I switched to this data set is that I just made a really, really small data set. Okay, so here's the edge. So there's the edges. So it really embosses those edges. That's something that's used in image processing sometimes. It's something like that. Okay. Now, what if we change this to 10 by 10? First of all, it's going to take more time to run. I'm going to call this edge 10. But now, it's looking for change over a larger area. And so, in order to be the biggest difference in the output and input, it will be looking for more change over a larger area. So it looks similar. Okay. But you can see, like in here, there's absolutely no detail in this area on the just plain old edge effect. But on the edge 10, now there's some detail in here. Because there is some change that's occurring over a 10 by 10 pixel. Even on that, you can see the texture out there. Okay. So, anyway, my point here was that you could take a data set and do some math on it. You can do any math. You can do add, subtract, multiply, divide. You can do functions like power, raise it to the power of, but you actually have to use a function for that, not use the same Python notation. Like star doesn't work. There's a function for it. Now, sometimes, like when you use Raster Calculator, you'll need to specify that you want to change your data from integer to float or from float to integer, and you can actually do that almost the same way you do in, like if I wanted to make sure both of these were float. I wonder if they are float. I forgot. I'm going to check here real quick. I'm going to go back to the original data set. These are already floats. Let's file, save as. I'll call this example 4. And just this one will be just be an example of changing the data type. So I'm just going to go like this and say WSB int equals int WSB DEM. I'm going to save that out. Oops. As WSB. By the way, I can change the format. Like if I wanted to save it as a .img, that's another raster format, I can do that right here. When you save it, you can specify the format that you want to save it in. I don't know why this one's taking longer to run. There it goes. I mean, that's shouldn't take too long. So in this area, oops, there's my anti-ng. So now, in this area, there's not a whole lot of variability. And so the reason that these are all the same color and these are all the same color is because they used to be the same elevation, but the decimal point was different. So now I've basically stair-stepped that slope there in front of the Walker Science building. And the trees, it's still kind of variable. I'm going to go to my code for a second. Seems to be people are looking at that. Okay. Now you'll notice that you don't have to type this in, but that's the way I would do it in Python, right? This int is actually a function, an ArcGIS function that works on rasters. The little int is a built-in Python function that works on numbers. So there's a difference there. So when you want to change it to an integer, you use big int. When you want to change a raster to an integer, you use big int. When you want to change a float to raster, a raster to float, you use big F, because that's a function that's built into ArcPy. So it's a different function that's actually running. And I don't know for sure, but I suspect the reason why ESRI capitalized this is so there wouldn't be a conflict between those two functions. Okay. Otherwise, you'd have to have put arcpy.sa.int if there were two functions named the same thing, if it was ambiguous. All right. Let me see what next thing I want to talk about was. Okay, we talked about the raster save method. Yeah, okay. That is this is actually one of the things I want to talk about. I'm not sure if it's the next thing on the list, but I'm going to talk about it right now. So, one of the really big gotchas in raster, and remember vector I think was harder, but this one can be puzzling, is working with extents and cell sizes. Okay? So if you're working with a single raster data set and making changes to that single raster data set, then you don't need to worry about this. But what if you're working with multiple raster data sets, or you're creating a raster data set, a new raster data set? In those cases, you want your raster data set that you either created or the one that you're using to match the current data set. Because if you take a raster data set and you add, subtract, multiply, divide it with another raster data set, and they are not the same area, by default, you're only going to get the overlapping area, and you're going to get the larger of the two cell sizes by default. So if you want anything different, you have to know how to deal with it. And this is true even outside of Python, okay? But you need to know how to program that. I guess what I'm trying to say here is, let's say I have two data sets, one that's at this area and another data set in this area. If I add those two data sets together, I'm only going to get this area right here. The result is only going to be those two data sets. Okay? That really does make sense that that's going to be true, but there are certain situations where you wouldn't expect to get that. Okay, also the cell size is going to match whichever one is coarser, and that is one that's, you may want to be able to choose. Okay? So this is what that's saying right here in this help. This is setting the environment extent. So as long as you set the environment extent, and you can also set the environment cell size explicitly in your code, then you'll always get the answer that you expect. Okay. So let's copy this, and did I already save this as a new example? I don't think I did yet. Save as example 5. Okay. All right, and this will show the utility of this as well. Okay, why this is important. Can we tell what units these are in? Let's go back to the original one. The original one is this one. These look like they're in feet from some zero mark somewhere on campus. They're not in feet above sea level. Okay, but the Walker Science Building, I think 47 feet makes more sense than 47 meters. Okay. So let's assume that these are in feet. So we're going to change the, I also have to say from arcpy import env. It's going to import the environment. Then I could actually just change this one. All right. The reason why I had to do that is because it just said env.extent. All right. One of the best ways to do this is to set your extent using an existing raster. So we're actually going to have to copy this down here. This line is actually not even necessary. That was from copying over from the other one. Okay. So if I copy this down to here, and I say WSB, WD, so the extent is a property of a raster. So here what I'm doing is saying, I want to take the WSBDEM, and I want to find out its extent, and I want to make that the extent of any new raster that I create, or the result of an output of any function that I do. Okay? I'm also going to change the cell size to be env.cellSize is going to be equal to WSB.cellSize. I'm pretty sure it's cell size. I want to make sure that it's not cell size with a capital S. Just a second. It is. Sorry. Okay. Cell size with a capital S. Like that. There are different values you can use. You can use the cell size of a specified layer or raster data set. That's the one we're using. You can also use min of or max of, or set it with a number. If you don't set anything, it's going to be max of as the default. Okay. All right, so now any data set that we create will have the same extent and cell size as the WSB DSM. So they won't grow, but you're like, well, the data set we created sure looked like it had the same extent and cell size, and it did have the same extent and cell size, but that's because we, by default, it on any of the data sets it operates with, it uses that same extent and cell size. Okay, but here, what I want to do on this example is say WSB meters. And we're going to change the WSB DEM, and we're going to add it to a new raster that is, not add it, sorry, multiply it by a new raster there we go, by a new raster that's empty. Well, not that's empty, but it's just a number. So this is possible. You can take a number, and if you use the raster keyword, it'll turn it into a raster that has that value everywhere. You can feed it a number. But it wouldn't be the proper extent and cell size unless we did this first. And so it would produce just a raster data set out there in space, but we don't want that. We want it to be a one by one. We want it to be across the whole data set. So now we're going to save this as WSB DSM meters. So it's going to save this data set out. Did I already save this? Okay. All right, so now I can run this guy. What's that? Whoops. Okay. Well, we just saved over the integer one then, if it was. Maybe it actually does take the path, is what it looks like. It doesn't actually take the raster, it looks like. Okay. Let me make sure, just a second. Recent files. 4. Nope, 4 was the integer 1, so we're good. We didn't save over anything. All right. So it looks like the cell size actually wants a path and not the raster dot extent. So it's not an object. You know what? I don't think raster is for, sorry. Raster is for turning a path. You can just use a number. That's the right way. Just that, you don't put raster around the number. That's for paths. This will work. But this will ensure that that is the right size. Of an object. Okay, it ran. And now, if we look at the data set, we will get a data set in meters, and it looks just like this, right? Those two data sets look the same, but if I actually click on the data, integer, then I'll get 13 and 14 for the top of the building, and that makes more sense. Right. Here, I'll put it back up here for a second. All right. Keep that up there for a second. I just want to make sure there's no holes in what I've talked about so far, so I want to look at my notes. Sometimes I print it out. Okay. I talked about arithmetic operations, but I didn't really talk about the con statement. It's a conditional statement. Most of you have probably done that in another class, but you can do that in ArcGIS. It's really almost the same. So I'll do this example 6. you could say, let's just call this con. So what this does is allows us to create a new raster where if the WSBDEM is greater than 30, give it a value of 1. If not, give it a value of 0. It's very useful for situations where we want to create a binary raster or have two different values in our output data set. I already renamed this, so I'll just run it. So this is just going to be a data set where if we wanted to ask the question, where are those areas that are greater than 30 meters, or 30 feet, because I went back to the, oh good. I went back to that one. Refresh, WBS. So I guess everything is greater than 30. That's not right. Or nothing is greater than 1. Let me go back to here for a second. Those are definitely, did I say less than? No. WBS, BBSM. Oh, yeah. Everything's greater than 30. Sorry, let's change this to 40. I'm going to click off of it and run it again. It's just that everything was greater than 30, so we just got a 1. But this might be useful, like if you're trying to make a land-water mask, and that, I mean, that just came up last week in on my trip. Where I went to analyze some data. We were looking specifically at the underwater data, and we didn't care about the land data. And so what we did was we said, you know, if the reflectance value matched a certain value, we assumed it was water. And so we set all those pixels to 1, and we set all the land values pixels to 0. Then we multiplied the original data set so that all the land pixels now had a value of 0, so it's like masking them all out. So here is here's that refresh data set. There we go. So these are all the values that are over 40, and these are the values that are under 40. Go back to that for a second. Okay. Any tool in ArcGIS can be run. Any of the tools in the Spatial Analyst Toolkit can be run. Some of them require setting up, like this one did. So you had to set up a neighborhood rectangle. But any of those tools can be run that exist in here can be run inside of Python. All right. There's one last thing I'm going to talk about, and that's the eval function. But I'll save that for the lab. So we'll talk about it during the lab. But basically, I'm going to introduce it right now. Let's say you have a bunch of rasters or a bunch of files in a list. Okay? And you want to create a raster calculator expression that adds them all together, which is what the lab is going to be. How can you do that? Well, there's not a real straightforward way to do that in ArcGIS. Like what I'm trying to say is, like, let's say I have WSBDEM1, WSBDEM2, WSBDEM3, but you have no idea how many WSBDEMs you have beforehand. You actually created them in a loop. There's really no way to construct a statement like this. But Python has the ability to take, where's my Python? There it is. Python has the ability to take a statement and actually construct a Python statement inside of it. So I can just go like 3 plus 5. Okay. Oh, it takes a string, that's right. So I could take a string, and as long as it's a Python statement, it will evaluate it and give me the result. So I can evaluate that and it'll give me 8. Now that is the same as going like this, right? The difference between this and this is the same. I mean, they're the same result, but this is a string. So I can construct a string dynamically and then execute it in Python. So we'll talk about that after we come back from the break. So let's come back around 3:15. Let's take a break about the same time we usually take our break. And then what we're going to do for the lab is actually loop through a bunch of data. And the reason we're going to need this logic is we're going to loop through a bunch of vector files, calculate the distance, add them all together. So we're going to have to practice using cell size and this eval statement. All right, I'm going to stop the